So the third piece of information that we should also know about all the atoms is their atomic mass. Now, if you remember correctly from a previous session, I said that the atomic mass of an element is given in the periodic table as a fractional number below the symbol of the element. Atomic mass of an element is defined as the relative mass of an average atom of that element. So there are a couple of terms here that need a little bit explanation. For example, what does it mean to say a relative mass? Relative, what does relative mean? Relative means something that is comparative, compared to something else is relative. Um, uh, I can say that the absolute weight of an orange is 1 pound, but the relative weight of that could be it's 2.5 times as heavy as a lemon, for example. So relative means it's compared to something else. Atoms are so small that we can't really determine their absolute masses, at least not yet. So what we have instead done is discussed or figured out each atom's relative mass compared to something else, how heavy is a certain atom. The other term that is important, a phrase that is important in this definition is average atom. Please remember in an earlier session we talked about isotopes and how almost all the elements in nature occur as mixtures of isotopes, and those isotopes are not present in equal quantities. The percent natural abundance, the percent fraction of each isotope in a sample of an element is something that is characteristic to that element. Nature decides that, we don't. So an average atom of an element would basically be an atom that is considering all the isotopes of that element present. So the atomic mass that is given in the periodic table for every element is the relative mass of an average atom for that element. It is in the periodic table, as we said, and also please remember that atomic mass does have a unit. Atomic mass is measured in units of AMU. AMU simply stands for atomic mass unit. So all atomic masses that we can read off of the periodic table are in units of AMU. For example, go ahead and if you look at the periodic table, can you tell me what is the atomic mass, the relative atomic mass of an average hydrogen atom? Yes, different periodic tables may give that number in different number of decimal places. We will round all our atomic masses, to 2 decimal places. So please remember to do that. Whenever you read any atomic mass from the periodic table, round these to periodic table, round these correctly to 2 decimal places. So no matter which periodic table you're looking at, if you round the atomic mass of hydrogen correctly to 2 decimal places, the atomic mass would be 1.01 AMU. Similarly, atomic mass of an average atom of iron would be 55.85 AMU, or iodine would be 126.90 AMU. So the atomic masses are relative masses of average atoms of all elements in units of AMU. The atomic masses, as we said, are relative. They are relative to the most abundant atom on the surface of the earth. They are relative to the mass of one atom of C12. C12 atom is the most abundant atom on the surface of the earth, so that is taken as the standard. And we have assumed that the mass of one C12 atom would be 12.00 AMU. So if the C12 atom has a mass of 12.000 AMU, then hydrogen mass would be 1.01 AMU, or nitrogen mass would be 14.01 AMU. That's what the relative mass implies. The atomic mass elements are, as we said, they are weighted averages considering all the isotopes of that element present in nature. Now, whenever we are determining relative atomic masses of elements, we must have three very important pieces of information. We must know how many isotopes exist for that element, the number of isotopes. We must also know the relative atomic mass of each isotope. So hydrogen in nature occurs as a mixture of three isotopes, H1, H2, H3. In order for us to figure out the relative atomic mass of the element hydrogen, we need to know that there are three isotopes. We also need to know the relative atomic mass of each of the three isotopic atoms, H1, H2, and H3, and we need to know the percent natural abundance of each isotope. Only when we are given these three pieces of information can we then calculate the relative atomic mass of that element. Please remember that the periodic table always gives the relative average. And when we say average, we do not mean simple average, we mean weighted average atomic mass of each element. Okay, so let's see if we can calculate what formula do we use to calculate the relative atomic masses of the elements that are available in the periodic table. Now, before we do that, I just want to highlight the fact that in order for us to calculate the atomic mass, the relative average atomic mass of an element, we need to know three things. We need to know, number one, the number of isotopes of that element that are in nature. We also need to know the percent natural abundance of each isotope. And the third thing we need to know is the relative, remember, to carbon-12 atom, relative atomic mass of each isotope as well. Only when you have these three pieces of information given can you then calculate the average atomic mass of an element by using the following formula. The formula is percent natural abundance divided by 100 times relative atomic mass for isotope 1 plus percent natural abundance divided by 100 times atomic mass for isotope 2 plus, and you keep doing that if there are more than two isotopes for a certain element. So this is the formula that we use to calculate the average atomic mass of an element that is given in the periodic table. Okay, let's try it out. Now here's a problem that talks about silicon that has a Z value equal to 14, and the question says that it has three naturally occurring isotopes. We know that the atomic mass, the relative isotopic atomic mass of the first is 27.977 AMU, and its percent natural abundance is 9.21. The second isotope has an isotopic atomic mass of 28.976 AMU with that percent natural abundance, and the third isotope has an isotopic relative atomic mass of 29.974 AMU. The first part of the question says or asks for us to calculate the mass number for the three isotopes of silicon. Now, at this point in time, I would like to give you a piece of information that we have not discussed before. A value, the mass number of an isotopic atom, of an isotope, equals its relative atomic mass rounded to the closest whole number. This is true for every isotope. The mass number for an isotope will be equal to the atomic mass of that isotope rounded to the closest whole number. So if you look at the first isotope, its mass is 27.977 AMU. If you round it to the closest whole number, that is 28. So the first isotope of silicon is silicon 28. Similarly, the second isotope has a mass of 28.976 AMU, which rounded gives us silicon 29, and the third one has a mass of 29.974 AMU that gets rounded to silicon 30. So the mass numbers of isotopes equal their respective relative atomic masses rounded to the closest whole number. Okay, let's read the second part of this question. This is part B and not part A. What is the percent natural abundance of the third isotope? Now, this question is basically designed to make you think that the total percent of anything can be 100%. So if you're given the 2 of the percent of the 3% natural abundances, you can calculate the percent natural abundance of the third isotope by basically subtracting the sum of the 2 given from 100. Percent cannot be more than or less than, total cannot be more than or less than 100. So that gives us 86.09% for the third isotope of silicon. Okay, you might want to pause the recording and take a little break at this time before we go on to the next problem. Okay, now that you're back, take a read. Let's read this problem. It says for us to calculate the atomic mass of chromium element using the data given below. Now look at the data that we know. We know that there are 4 isotopes of chromium. So that's given to us. We know that each isotope has a certain percent natural abundance. We're given that. We're also given each individual isotope's relative atomic mass. Now, one thing that I would like to point your attention to again is, look, if the atomic mass of an isotope is rounded to the closest whole number, that gives us the mass number of that isotope. That's only true for isotopes though. Okay, so let's use the formula that we wrote down earlier to calculate the average atomic mass of chromium, average relative atomic mass of chromium using the data given. So if you remember the formula, 4.31 divided by 100 times 49.9461 plus 83.76 divided by 100 times 51.9405 plus 9.55 divided by 100 times 52.9407 plus 2.38 divided by 100 times 53.9389. So we are substituting the percent natural abundance and their relative atomic masses for each element, each isotope of the element that is given. If you solve these using a calculator, and please go ahead and pause the recording while you do that. When you have done that, hopefully you get the first one to be 2.15267,691 plus 43.5053628 plus 5.055836885 plus 1.28374582. Now, note that the next step after this is an addition step. So far, all we've done is multiplied and divided, but the next one is going to be plus, which has different set of rules as far as significant figures are concerned. So we do need to round at this stage. We do need to use a sig figs and round. The first answer has to be rounded to 3 significant figures because of that. The second one needs to be rounded to 4 significant figures, the third to 3, and the fourth to 3 as well. So we need to round each of these to the correct number of significant figures, which gives us 2.15 plus 43.51 plus 5.06 plus 1.28. And then when you add these together, since we get an answer of 52.00, you have to give this answer in 2 decimal places because each of your add-ins, the numbers you added together, had 2 decimal places as well. So please don't leave this as just 52. It needs to be 52.00 and then the unit AMU. Now go ahead and check the periodic table and see what is the average relative atomic mass for chromium in the periodic table rounded to correctly to 2 decimal places. Is it 52.00 AMU? Yes, it has to be, because once again, please remember that it is this number that goes in the periodic table for every element. Okay, let's go on to the next slide, and once again, pause the slide, pause the recording while you read the problem and try to attempt it. What you are given in this problem is that we are talking about magnesium first of all. We are also told that magnesium has 3 isotopes. We're given the details of magnesium 24. We're given the details for magnesium 26, but we are only given the percent natural abundance for 25. They're asking us to calculate the relative isotopic atomic mass for magnesium 25. So if we substitute the data given, let's do it into the equation. Let's see what that looks like. Now, we know that the relative average, the relative average atomic mass of the element equals percent natural abundance 78.70 divided by 100 times its isotopic mass for the first isotope plus percent natural abundance divided by 100, but we don't know its isotopic atomic mass. That's what we have to calculate, so we put an X there, plus the third isotope 11.17 divided by 100 times 25.983 for the third isotope. So we do have a variable X, but in order for you to solve this equation, you need to be given that value, average atomic mass. Where do we get that from? Yes, absolutely. Please remember that this comes from the periodic table. If you need that value for calculations, then you can get it from the periodic table. So if we round the periodic table atomic mass of magnesium to 2 decimal places, we get 24.31 AMU. And let's solve each of those factors. So we get 18.876195 plus 0.1013x plus 2.9023011, which leads us to 21.778491 plus 0.1013x, which gives us 0.1013x equals 2.531539. That means x equals 24.990. Since it's an atomic mass, the unit has to be in AMU. I chose to write this in 3 decimal places because the given atomic masses of the isotopes are also in 3 decimal places. Okay, let's go on to the next question. Once again, please do stop the recording, pause the recording while you read the question and attempt it on your own. Now in this problem we are told that we are talking about nitrogen, therefore we can use the atomic mass of nitrogen, average atomic mass of the nitrogen element, which rounded correctly to 2 decimal places gives us 14.01 AMU, equals the first isotope is N14. We know its atomic mass, but we do not know its percent natural abundance. So let's assume that the percent natural abundance of nitrogen 14 is X percent. If this is X percent, what would be the natural abundance of the second isotope of nitrogen? Absolutely. Please remember the total percent has to be 100. So the percent natural abundance for the second isotope, if there are only 2, would have to be 100 minus X percent. Using these, plugging them into the equation we used, we get X divided by 100 times 14.003 plus 100 minus X divided by 100 times 15.000. If we solve this, if we simplify this, do the distribution that we need to do, we come up with 0.14003x plus 15.000 minus 0.15000x. And all of this is equal to, of course, 14.1 from the periodic table. If you simplify, you take this number on the other side and add the similar ones, we get minus 0.98599 equals minus 0.00997x, which gives us x equal to 98.90%. And please remember, we assumed the percent natural abundance of nitrogen 14 to be X. So the percent natural abundance of nitrogen 14 equals 98.90%. And if that's the case, percent natural abundance of nitrogen 15 will be 100 minus 98.90 comes out to be 1.10%.